Okay, welcome to the third lecture for Internet of Things. Hope you can see my screen. Today we're going to talk about the physical layer and maybe some notions that you've already met in some of the classes, but I just want to make sure that they are well covered for every student in the course. So it's about wireless transmission fundamentals. We're going to talk a lot about antennas. We're going to talk a lot about propagation. We're going to talk a lot about radio spectrum and so on. So the physical layer, as you probably know, it's the base layer in any ISO-C stack for applications, transport network, data link, and physical. That's the that's the stack of applications and protocols that run on software and hardware that runs on a computing device. Um, Now we're gonna make a brief introduction about RF in general, what is radio frequency, and how we can use it for communication. Uh, the lecture is going to be filled with wireless terminology, so you're going to hear a lot about power transmitter. You're going to hear a lot about parameters such as RSSI. You're gonna hear a lot about packets, frequencies, ranges, things like this. And we're going to finish up with antennas and signal propagation. So we're going to briefly talk about antennas. We're going to briefly go through some propagation models for different antennas and how they affect the RF range and RF propagation of signals. Now, these notions might be, like I told you, well known for some of you. So just briefly, let's go through them. Wireless communication usually is done in a frequency range from let's say 100 kilohertz to around 60 gigahertz. So it's the band of communication that usually is reserved to radio signals. So it's less than let's say the frequency of light, and a bit, quite a lot bit more than the frequency of acoustic vibration or sound. And you have some examples here of different frequency bands. So for example, we've got low frequency signals. You get I don't know, 50 hertz, for example, which is the house electricity we all use. And then we've got high frequency. This is where radio starts basically, and how different frequency bands are actually done for wireless communication, television communication, satellite communication, wireless emitters, receivers, usually for to actually ensure a high bandwidth, they use the gigahertz range of communication. So we're looking at 2.4 gigahertz, 5 gigahertz, and so on. Anything more than this is usually in the spectrum of microwaves. So more than 10 gigahertz is usually considered as a microwave signal. So these frequencies or frequency bands are usually regulated. So you have here some examples of the most encountered, let's say, frequency bands in different countries. Europe has its own standards. USA has, again, its own standards. Japan and other countries have their own standards as well. It's usually they're overlapping, but not necessarily and not in all cases. So, for example, for cell phones in Europe, there are these standards of communication frequencies, and these are in megahertz, all of them. So from 450 to 457 megahertz up to 960 megahertz, and then more 1.8 gigahertz, and so on, depending, of course, on the bandwidth and on the um, distance and the modulation type adopted by the radio transceiver in the cell phone. Uh, Similar frequency ranges are available in US and in Japan, but as any phone manufacturer knows, they need to adapt their radio transceivers in order to actually emit in these frequencies for them to be compliant with regulations in all countries. Same as wireless LANs, these are more or less overlapping here for countries. So we've got the 2.4 gigahertz frequency band which is pretty much identical in Europe and in US, but there are some modifications to the band for Japan, for example. So it doesn't necessarily start at the same frequency or end at the same frequency. So basically, these are frequencies where you can emit for commercial applications where you might need a license, or for short ranges you might not need a license, such as for a Wi-Fi emitter or a Bluetooth emitter and so on. Okay, so some basic concepts, and you might hear about them in the next slides. RSSI is radio signal strength indicator. It's a measure of how powerful the received signal strength is for a certain radio receiver. dBm, it's decibels milliwatt. It's a measure of power. And we are measuring power in radio usually in decibels. So this actually allows us to, convert a linear scale to a log scale in order to accommodate, very large band of powers, from very low powers, such as 10 to the maybe minus 12 watts, to, powers of watts or hundreds of watts. Again, we might talk about noise floor, duty cycling, LPL, and so on. So these are all notions that you're going to hear within this lecture. Signal transmission usually is affected by noise. So this is a phenomenon which happens in every data transmission equipment. Usually have the original signal, which might be even a digital one, so discrete levels of zeros and ones. And then you have some noise that is actually affecting the transmission channel. It might be a wired channel, it might be a wireless channel. It doesn't necessarily matter. What actually happens is the noise overlaps the signal. So you have a composed, let's say, signals plus noise reception at the other end that you actually need to sample, and you need to recover the original signal from. So usually when there's a high quantity of noise overlapping the actual signal, in this case a digital signal, it might actually flip your 1 or x bits. So for example, here you have two 1-bit errors that actually are caused by noise. So a lot of noise actually flips this bit from 0 to 1, and again, a lot of noise in the channel flips this bits from 1 to a 0. So this is why, especially in radio communication, you have a lot of error detection and correcting codes to actually cope with this, because noise is inherent to any communication channel. And of course, when you detect that the communication channel is actually affected by a high degree of noise, most modern wireless transceivers, they usually adopt a lower frequency, or they change the frequency of emission, or they actually can change the data rate on the communication channel. They can change the modulation to actually better cope with an increasing level of noise. Usually data is sent within packets. So this is kind of like the anatomy of a packet for transmission and reception. The data is actually assembled in these packets and sent over the communication channel. Uh, what is a signal? Well, you might ask. Usually it's an electromagnetic signal, so it's a function of time. It varies in terms of amplitude in function with time, and it's also a function of frequency. So a signal might consist of components of different frequencies. So it's not only a single frequency, but rather a composition of multiple frequencies that actually achieve the desired effect. So for example, we've got let's say the main frequency channels or ranges for 802.15.4 standard physical layer. So this actually specifies the operational frequency bands for transmission for this particular standard. So any RF transceiver that adheres to this standard needs to actually have capabilities of transmitting in at least one of these channels. So you've got first 868 or 915 megahertz frequency range, where you have a single channel at which is centered around 868.3 megahertz. Again, it's not only this frequency, but rather a range of frequencies, which you can see actually in channels 1 to 10, which are spread equally between 902 megahertz and 928 megahertz, with a spread of 2 megahertz between them, so not to ensure they're not overlapping. And then they on the 2.4 gigahertz, sorry, range, you've got other channels from 11 to 26 in total, again spaced 5 megahertz each, from 2.4 gigahertz to 2.4835 gigahertz. So this ensures that not only can you communicate and you don't have overlap in the 2.4 gigahertz range of frequencies, so you can have multiple emitters and receivers here that don't actually overlap in this range, so you can accommodate a lot of these devices in a relatively small space. But also, if there is some sort of noise affecting the transmission, then you can switch to a lower frequency. Usually that helps. And you can actually have some channels there. You have 11 channels that you can choose from and send data. Of course, the bandwidth is more limited in this frequency range. So spectrum, bandwidth, and the channel capacity. It's a link between these. So usually the channel capacity tells you the maximum number of bits that can be transmitted per second on a physical channel. So it's a nice formula that actually specifies this, where W is the frequency range of the channel, so exactly the interval of frequencies which is used by the communication channel, and then S over N is the signal to noise ratio. Assuming let's say a Gaussian distribution of noise or a normal distribution of noise, you can actually compute how many bits you can actually send per second over a physical channel with this formula. Uh, you've got here, let's say, spread of most used frequencies for communication in radio emitters and radio transceivers. So you've got frequencies from, like I said, roughly 20 kilohertz or 30 kilohertz. This is where very low frequency stands, to almost infrared. So extra high frequency, or THF, you even have THF or tremendously high frequencies between radio and where light starts to actually happen. So it's no longer radio emissions, it's light emissions in infrared. So you've got different bands. They're all, let's say, categorized for their frequencies. So starting from very low frequencies to very high frequencies. And you've got this very nice formula that you might remember from high school, that there's a direct link between wavelength and frequency. And it's, wavelength is c, where the c is the speed of light, over frequency. You can convert one to another. So why don't we send digital signals in wireless communications? Why don't we just send a series of ones and zeros over a radio channel, and instead we adopt a modulation scheme and we actually encode our bits like this? Well, it's a simple question of computing exactly a signal of frequency, of a given frequency. If you would like to actually transmit it over let's say a channel. So for example, you take voice. Voice is actually spread in a bandwidth between 20 hertz and 20 kilohertz, and you would like to transmit voice like this. Well, the antenna usually is directly proportional to the wavelength of the signal. So let's take a frequency range from the audio spectrum So 3 kilohertz is within the medium range of the audible spectrum. And see, for this frequency, what the wavelength is. So just by plugging this into the wavelength formula, you get that the wavelength is around 100 kilometers for the 3 kilohertz frequency. So then you will need to have, in order to transmit a signal at the frequency of 3 kilohertz, you will need to have an antenna which is around 100 kilometers long, or at least tens of kilometers long, in order to effectively transmit this sort of signal. So the antenna is too large. It's impractical, to say the least, to actually send signals directly without them being modulated over a carrier signal of a higher frequency. So usually what we do, we use this modulation to actually transfer to a higher frequency, where we can actually have antennas which are a lot smaller in size, and radio communication can be practical. So some basic concepts of modulation, which you probably might have heard in some other lectures. Usually, you've got a low frequency signal. This is referred to as a baseband signal, which is actually overlapped on a carrier. So you've got a higher frequency. Usually, it's a sine frequency, or a sine function for it, something like this, and you actually modulate this lower frequency signal over this higher frequency sinusoid signal. So you've got the baseband and the carrier, they both go into a modulator, and out comes the modulated signal. Uh, so what does it mean that you've got a modulated signal? It means that some parameter of the carrier, and the carrier might have different amplitude, different frequency, or a different phase. This is varied in accordance to the baseband signal. So a stronger baseband signal means maybe a stronger amplitude. A lower baseband signal might mean a lower amplitude of the carrier signal, when you have amplitude modulation, for example. So there are different types of modulation. Usually analog modulation is amplitude, frequency, and pulse modulation. So it's AM, FM, and PM, or double and single sideband, DSB and SSB. Digital modulation, however, you can actually modulate signals in digital form by modifying the amplitude of the carrier signal in discrete levels. So you've got maybe an amplitude level for a 1, and a different amplitude level of the carrier signal for a 0. And this is called amplitude shift keying, or ASK. You can actually modulate it in frequency. So you have a different frequency for a 1 and a different frequency for a 0. Then you have frequency shift keying. You can have phase shift keying as well, and it's binary phase shift keying, quadrature phase shift keying, and so on. And quadrature amplitude modulation, you can actually modulate the signal in more than 2 levels of amplitude. So these are all notions that you probably heard of when you were talking about radio communication in the radio protocols course back in bachelor's. So I'm not gonna actually insist very much on those. Just to give you an example of how amplitude modulation works, you've got a block diagram here where you have the baseband signal, and you compose it with the carrier signal, and out comes the modulated signal in amplitude. Very simply put in graphical form, you've got this is the baseband signal, and this is the carrier signal modulated with the baseband signal, and you can actually see that the carrier signal is of a higher frequency, and then the amplitude varies directly proportional to the amplitude of the baseband signal. So higher amplitude of the baseband signal, higher amplitude of the modulated signal, lower amplitude corresponds to lower amplitude in the baseband signal. And you can actually decode this and recover the baseband signal from the modulated signal in a radio receiver. In a frequency domain, what you have is actually composing So actually, from the baseband signal, you actually get two or more frequencies for the modulated signal. Now, in wireless terms, you've got, like I told you, a power and other parameters which are measured in relation to decibels. Decibels usually are a ratio of two powers. So, for example, if you'd like to have a ratio of power 1 to P2 in decibels, then you actually apply this nice mathematical formula 10 times log base 10 of P1 over P2. So this is the decibel measure of these two powers. These two powers now are expressed in watts, and what comes out is power expressed in decibels. Now, we've usually got, when we're talking about power, we've got dBm, or decibel milliwatt, because the second power is always the reference, and this is the reference to 1 milliwatt of power. So whenever we have one single power and we'd like to reference it to something and we'd like to express it in dBm, we reference it to 1 milliwatt of power. Again, we've got signal to noise ratio. That's a measure of how noisy the communication channel is. And again, it might be expressed in, using power expressed in decibels. Attenuation of the signal over communication channel usually means power loss, again, measured in decibels. CDMA, again, it's a notion that you might find in the next slides. It's called code division multiple access. Simplex or duplex communication means, simplex means that we have a one-way communication, so we only have a receiver and a transmitter. So it's not done in two ways, and at least not, in a single instance of time. Duplex communication means that you have different channels or simultaneous channels for reception and for transmission for a signal, and you can receive and transmit at the same time certain signals. The FCC is the body that actually regulates communications, radio communications of any kind in the United States. So you're probably going to see again this abbreviation. It stands for the Federal Communications Commission. Antenna gain, how much power the antenna received, is actually compared to a reference. Again, expressed in decibels. MAC, probably you've heard of this abbreviation. It stands from medium or media access control. Again, some other terms. Circuit switched. It's a virtual link between different parties, and the connection is held even when no actual data is transmitted. So you actually keep the connection alive. Packet data is how we actually split information within packets. We packetize it and route it through a communications network. Spread spectrum, again, it's a notion of wideband modulation, which actually imparts noise-like characteristics to an RF signal. Frequency hopping and direct sequence, these are examples of spread spectrum communication. You've got TDMA and FDMA, time or frequency division multiplex access. Again, terms that are used here. Now, going through different analog and digital links, we've got another term which is usually employed. It's BER, stands for bit error rate. This bit error rate usually increases as the signal to noise ratio decreases. So you've got more noise on the channel. Usually the effect is that you've got a higher error rate in transmission of digital signal. So this is why we usually employ error detection and correction mechanisms in radio transceivers. We actually can repair or have, let's say, some sort of redundancy in radio transmission by repeated transmissions. So if a packet did not go through, then we send the same packet twice or as many times as necessary until it's received. And or we reduce the channel capacity. So we employ a different type of modulation over the same radio channel, or we switch to a lower frequency or a higher frequency band in hopes that the signal to noise ratio will be different. Um, Now, there are different models or mechanisms for radio propagation, and we will talk about them in the next slides. There's the free space propagation mechanism. There are different phenomena which are actually affecting radio transmission. One of them is reflection. When a wave impinges on a large object, then it usually can reflect over that object. So it's maybe a phenomenon which is analogous to what happens to light when it hits a mirror, it reflects over that surface. Diffraction, how waves can bend around obstacles, and even when you've got no line of sight between the receiver and transmitter, you can actually, through reflection and diffraction, you can actually communicate between those two. And you've got scattering, when a signal actually uh, comes across an object which is much smaller than the signal's wavelength, then you usually have scattering over that object. So there are simple but very useful models for free space and common geometries, such as flat surface transmission over a flat surface, curved dirt surface, a wall, and so on, which can approximate radio transmission in different environments. And again, the radio propagation in real environments might be a very complex problem to solve. So there are simulators which actually try to approximate what the radio propagation might be in a real simulated environment, where you've got multipath propagation, you've got shadowing, you've got attenuation, you've got different phenomena which actually come and can actually affect communication between a receiver and transmitter. So there are also environmental changes, fluctuation in environment parameters that actually can also change the received power. So let's take the simplest model possible, which is the free space model, where you have a transmitter and a receiver. Usually a transmitter has these parameters. So you've got an antenna, the transmitter, which has a certain height. You've got a signal which is emitted by the transmitter with a certain power measured in dBms, and a certain gain. The transmitter is situated at the distance of r meters, let's say, from the receiver, which again has an antenna of a different height, and it usually can receive the transmitted signal with a different power, PR. This is the received power of the signal, and it can amplify the actual received power with a gain, GR. So you've got a free model where the transmitter and the receiver are in space, basically without any atmosphere or other objects actually impeding propagation of the signal. So it's a very basic model of propagation. And we've got this equation which actually, when we look at it, you can actually compute the received strength or the received power of the signal uh, through this really nifty equation. So you've got the received power is equal to the transmitted power times the transmitted gain, times the received gain, times this factor here, which is depending on the wavelength of the signal and the distance between the receiver and the transmitter. So you can use this formula to actually measure the received power of or the signal strength of the receiver. So you've got this model, which actually works when you are talking about free space isotropic signal propagation. So what does that mean? Free space, it means that you've got actually let's say an ideal vacuum between the receiver and the transmitter, and you've got no other objects that interfere between the receiver and transmitter or otherwise in the space that the receiver and transmitter are actually occupying. Isotropic means that the medium is the same in all directions, so it's got no variations in parameters in all directions, and the actual antennas of the receiver and the transmitter are ideal, so they propagate the signal equally in all directions, which of course is a very rough approximation of what happens in real life. So what can we derive for this formula? I mean, we've got this factor here, lambda over 4 pi d, where d is the distance between the receiver and the transmitter, and it's all squared. So if it's squared, then it means that in free space, the receiving power is proportional to 1 over the distance squared between the receiver and the transmitter. So in other words, the signal degrades over time in power with this relation of 1 over d squared. So the closer you are, the better. The farther away you get, you get a very powerful loss in received power. So sometimes we actually in order to actually get this ratio of received power over transmitted power, we can express it in log scale because the differences are so high. So imagine if the distance is big, then even if you transmit with a power of, I don't know, maybe a few watts, the received power might be in the order of microwatts or milliwatts. So it's at least 3 orders of magnitude less. It might be 6 orders of magnitude or more less than the transmitted power. So when you have these very big variations in received over transmitted power, then you usually express them on a log scale, so they can actually be normalized. So you use this expression where you have the path loss. So actually the loss of power over the path from the transmitter to the receiver, and you've got this expression which ties the two together, and again it's let's say on the log scale. What happens when you change the radio environment, and now we don't have a free propagation model, but you also include, let's say, a ground level or a plane, a ground plane, where the transmitter and the receiver sit on. So again, it's the only difference between this model and the free space model is the fact that we've got this plane here. Uh, we've got the same distance between the transmitter and the receiver. And what this changes is the fact that you've got some or part of the signal that actually reflects or can reflect from the ground plane and actually undergo a phase shift when it reflects from the ground plane. And at the receiver, you will not only have the original signal, which is clear line of sight from the transmitter, but you will also have this reflected signal from the ground plane. And now the equation changes a bit. So you see you've got here the received power, depending on the transmitted power and the distance between the two. You've got a dependency over not the distance squared, but the distance at the fourth power. So it's the power of the signal is degrading, much faster because of this. You've got as parameters diffraction as well, which is affecting the transceiver and the receiver in this in this model, where apart from the ground plane, we can also introduce some obstacles between the transceiver and the transmitter and the receiver. And depending on the distance between the transmitter, this obstacle, and the distance between the obstacle and the receiver, you can see here that you've got different zones. They're called Fresnel zones. And you might have times where you have direct line of sight, or you don't have direct line of sight between the transmitter and the receiver because of the obstacle that is sitting between them. This is all depending, of course, on the distance, distance d1 and distance d2, and you can actually compute the these Fresnel zones depending on the frequency of the signal and these distances. You can actually get if you have line of sight or if you don't have line of sight. For example, when you've got 2.4 gigahertz link, and there are the emitter and the receiver are 1 kilometer from each other. The antennas are each 2 meters above ground. We can compute if we have line of sight or if we don't have line of sight for these two. So if you plug in the numbers in the formula from the previous slide, you can get this evaluation of Fresnel zone. So it's roughly 5.59 meters. We actually apply to this the 60% rule. So if we compute what is 60% out of this distance, we get 3.3 meters. So 3.3 meters means that the antennas are too small to actually have direct line of sight. So if we had antennas which are maybe 4 meters in height, then we would actually have direct line of sight. So the answer right now is no. For this particular link, in this scenario, we don't have direct line of sight between the emitter and the receiver. So there are different loss models in radio propagation, from the free space model, which is the simplest one, where we saw that path loss is actually directly proportional to the inverse square of the distance, to, let's say, open areas, suburban and urban environments, where, of course, path loss is much more pronounced. So usually it depends on some sort of a power, 1 over distance at a certain power. So 1 over maybe distance at the third power, at the fourth power, and so on. And if the environment gets more and more crowded, usually that power factor actually increases. So it's just by looking at how indoor propagation works, we can see that actually the radio signal decays much faster. And this is, let's say, a scenario in which a lot of IoT applications actually operate, because you've got an indoor scenario, maybe at your home, where you have different radio emitters and transmitters that each occupy the same frequency band, and the propagation model is actually affected by different obstacles, walls, and ceilings, and so on, that are in that home environment. So it's a very complicated dynamic, especially when devices move within this environment. So people carrying those devices might move, and they can change the parameters of propagation through this environment. So usually when that happens, you have a very good estimation of path loss by this formula. So you can actually estimate how much in power you lose from the transmitter to the receiver. And you can estimate it basically, rule of thumb, by by this formula, where you have K as the number of floors in a building, F again related to the number of floors, walls, and it's W, it's a parameter of how much power is lost when the signal is actually crossing a wall. So for example, you have some metrics here, roughly estimated. So for different buildings, from retail stores to factories and homes, for different frequencies, you have a different value for the n exponent of the path loss formula, and then you've got different variations in signal strength and propagation for these environments. So usually it's to the power of 3, or maybe if it's a very, very crowded environment, a lot of noise, then it's to the power of 4. Okay, decibel, if I might might talk a bit more about decibels, they express a relative difference in signal strength. So you've got usually a formula for a decibel. It's 10 log to the base 10 of a ratio between 2 powers, When you've got 0 decibels, that means you've got no attenuation. So usually, the ratio between P1 and P2 is equal. So P1 is equal to P2. If you have 1 decibel of attenuation, that means 0.79 of the input power survives. So 79% of the input power survives, because that's what, if you plug into this formula, that's what basically gives you 1 decibel here. Again, 3 decibels of attenuation, 50% of the input power survives, and 10 decibel of attenuation means that 10% of the input power survives. You can find out more about decibels, of course, if you go to these links. It's pretty straightforward. So attenuation usually is measured by this formula. We actually can use attenuation in this formula as well. We don't have power, but we have voltages, and we measure the voltages. We only change the multiplying factor here. So as an example, if you have two powers, one is 10 milliwatts and the other one is 5 milliwatts, we can actually compute the attenuation to be at 3 decibels if you plug in these values in the formula above. And another example here for you where you have the attenuation computed at 20 decibels now. So it's really easy to actually change from the, let's say, linear scale to the log scale using this nifty formula. Shadowing is, again, a phenomena which happens in radio propagation. So this actually means that the signal strength is lost after the signal is passing through an obstacle, so through a wall, for example. And you have here some typical examples of shadowing. So attenuation of the signal or loss of the signal in decibels when the signal passes through different environments. So a window in a brick wall, a metal frame, an office wall, and so on. So you can see, it's more decibels when the medium is very thick. So for example, a metal door in a brick wall, you have, a very high shadowing factor here. So, it's a very powerful signal strength loss. And less of a signal strength loss when you have holes in the medium where the signal can propagate through. So dBm, as I told you, is the reference quantity in relative to 1 milliwatt. So dBm is actually when P2 is at 1 milliwatt, when you have one single power. So for example, you've got 0 dBm, of course, when P1 is also 1 milliwatt. And if P1, for example, is very low, so something 10 to the power of minus 11 watts, so 10 picowatts, then you've got minus 80 dBm. So you've got a very, very low power that actually can translate to a number which is not so low. So that's the idea of translating everything into dBm, because you have a very large spectrum of powers here, from picowatts to watts or maybe kilowatts of actual power, and you can actually transform that interval into a much smaller interval of decibels. So from minus, I don't know, maybe 100 to plus, I don't know, 10 or 20 or something like this. And you can plot these a lot easier. As I told you, received signal strength indicator, or RSSI, is the strength of a received RF signal. And there are many current transceivers, so radio emitters and transmitters, that can provide this hardware indicator. So for example, there is let's say maybe a chip in radio mode or a wireless sensor node that can actually measure this parameter, and by measuring it, you can actually get some or take some decisions in routing of packets through the network. There's also LQI. You might find it as such. It's called link quality indicator. It's a measure not of the received signal strength, but a measure of the chip error rate. So the transmission error rate between the emitter and the receiver. So it's the rate at which errors occur. So if you have, of course, a signal with higher LQI, it's far better than a signal with a low LQI. And then again, you can take some decisions when you are routing packets through the network. So for example, you can establish a connection which has a better LQI than another. So you can make some decisions. Noise floor is the measure of the signal created from the sum of all the noise sources and unwanted signals. So it's a accumulation of all noise parameters, all noise signals. And you got then the signal to noise ratio, which we've used in the previous slides. It's the ratio of the power in a signal, in an effective signal, to the power contained in the noise, in the whole noise that is present. So usually it's measured not at the sender, but at the receiver, because there you can actually compare it to the actual received strength of the signal that is sent. So you have some examples here for a certain radio transceiver chip. So you've got a noise floor that is actually measured from a register in the device. And it's the receive signal strength indication when the device does not receive a data packet. So for example, we measure it at, I don't know, maybe minus 98 dBm. So it's a very low noise floor. And then the strength field from the receiver packet is the actual RSSI when the chip receives a packet. So you can compare the two and actually extract the signal to noise ratio. Uh, okay, RSSI again is usually a number uh, that is used by the onboard software to actually take some decisions. So you can actually map the RSSI to dBm. And some of the manufacturers, some of the chip manufacturers can give you formulas in the chip that data sheet to actually have this, let's say, relationship between the number and the dBm power, but you can also have it directly expressed in dBm. So usually what we do with RSSI is we detect if, for example, in a mesh network, some links are better than others. And we can actually decide to route packets through preferential links which have a higher RSSI. So the higher levels in the stack, the operating system or the application might decide if an RSSI is too small for a reliable link, and then it can actually disconnect that link and try to connect to other devices which are in within range and have better RSSI parameters. So you have here some examples of how this can be actually interrogated from the application or the protocol that actually establishes a connection between two devices. And you have a plot, a very nice plot here of how the RSSI value actually translates into dBm. So there's not, let's say, linear relationship between the two. Usually it's kind of like a dependency, it's curve dependency like here. Um, so, for example, if you measure it and you can actually estimate your RSSI at minus 80 dBm, that means when you actually plug it back into the log formula and you reference it to 1 milliwatt, it means that it's the received signal strength is 0.01 nanowatts, which is very, very small. So this is the effective received signal strength of the transmitted signal. Okay, questions so far? Okay, now let's go on. Switching over to antennas. So we've talked briefly about antennas in the propagation model, where we talked about the antenna height for a receiver or the transmitter. What is an antenna? Usually it's a conductor that carries an electrical signal and radiates it as a radio frequency signal. The RF signal is a copy of the electrical signal in the conductor usually. So also the inverse process happens. So whenever RF signals are received, they are captured by the antenna and they create an electrical signal in the conductor that can be interpreted or decoded by the receiver. So that's why you have a very strong, maybe a very powerful electrical signal at the transmitter that is actually radiated as RF signal from the antenna, and then that signal is captured by the receiver, which has its own antenna, and the signal which is received is actually a copy of the transmitted signal, but at a far less power. So it's far less powerful, like you've seen in the previous examples. So the efficiency of the antenna depends on its size. Uh, Usually the size is relative to the wavelength of the signal. So for example, you can have a half wavelength antenna or a quarter wavelength antenna or a full wavelength antenna, depending on the design and depending, of course, on the application and on the frequency of the signal, which is actually used as a carrier for the transmission. So there are different types of antennas, and you probably are familiar with some of them because you have seen them or used them in different applications. The ideal antenna is a point source that radiates with the same power in all directions. So it's called an omnidirectional or isotropic radiator, but that's an ideal case antenna. So the antenna that transmits equally in all direction is called an isotropic one. So isotropos means it radiates equally in every direction. It's the same in every direction. But the shape of the conductor usually tends to create a specific radiation pattern. So depending on how you actually shape the antenna, it will have a different pattern. So you can have here a brief, let's say, description of what an isotropic radiator means. You have a point-like antenna, which is at the center, and then you have the signal which propagates equally in all directions. So you can imagine it in 3D space as a sphere. Whenever you have a directional antenna, uh, then the signal does not propagate equally in all directions, and you have maybe something like in this case here, where you have a preferential direction for propagation, which is this one, and then other lobes or other spikes in other directions. You can have let's say, omnidirectional antenna, which is a close approximation to an isotropic radiator, which is the ideal case, in which case you have, let's say, a better spread or a better propagation of the signals in all directions, but it's not necessarily equal. So the most common shape of the antenna is a straight conductor that's usually employed in many IoT applications because it's very cheap to construct an antenna of such form. But there are other antennas that can be used to direct energy in a certain direction. So for example, a parabolic antenna is a very good example of a directional radiator. So it radiates direction in the energy, preferentially in a forward direction. Uh, there are different signal propagation ranges which actually affect how a signal is propagated, and we can actually measure them. So between a sender and a receiver, we can have, let's say, different ranges. The first range would be the transmission range, where communication is possible and we have a relatively low error rate. Then you can, after this transmission range, you can have a detection range, where you can detect that there is a sender there, but you can actually not make direct contact with the sender. So because of the distance and the signal to noise ratio, you cannot actually have an effective communication rate with the sender. And after the detection range, you have the interference range, where the signal is so weak or so degraded that it may not be actually detected, because the signal actually adds then to the background noise and it becomes noise itself. So in signal propagation, usually in free space, it you can approximate the signal propagation in free space as light propagates in free space, so usually in a straight line. Um, and in that scenario, then you have the receiving power, which is proportional to 1 over the square of the distance in vacuum. That's in an ideal scenario. In a real environment, the received power is influenced by different factors. Fading is one of them, for example, shadowing, reflection, scattering, diffraction, and so on. You have here some examples of how shadowing, how reflection, refraction, scattering, diffraction can actually affect the signal and the propagation of the signal in certain media. So in propagation, it degrades the RF signal. You have the attenuation in free space as the distance becomes larger and larger from the emitter, then the signal gets weaker and weaker. And you've got that model of 1 over d squared that actually explains how the signal gets weaker. Again, you have free space loss because the signal spreads out over a larger and larger, ever expanding area. Uh, and whenever you have, for example, not vacuum, but other mediums, such as an atmosphere between a receiver and transmitter, you can have also absorption of the signal and refraction of the signal. Uh, of course, any other obstacles, they can weaken the signal through absorption or reflection. So any obstacles between the two, the receiver and the transmitter, they can actually affect the signal strength. Uh, you have multiple path effects as well, and you've also have mobility, which affects the propagation of the signal and the degradation of the signal. So whenever the receiver, the transmitter, or both, they move in the environment, the parameters can be affected. So you have here a schematic representation of how the received power of the signal actually decreases or increases with the distance between the two entities. You can also have the multipath phenomena where a signal can take many different paths between a sender and the receiver due to phenomena such as reflection, scattering, diffraction, and so on. So this can happen in a very common environment, a building, for example, where you have a transmitter in one room and the receiver in another room, and you have a wall between them. You can have reflection of the signal in these walls. You can have scattering over a window, for example. You can have diffraction over the edge of the wall here, and you can also have fading. So the signal can pass through the wall. And all of these signals, they compose when they reach the receiver. So the receiver not only gets the original signal, which actually is faded through the wall, but all these signals as well. And of course, the quality of the signal is affected by this because there might be of different phases, they might be of different amplitudes, and they all compose to actually give you the received signal. Multipath propagation means that a signal can take many different paths between the sender and the receiver due to these phenomena of reflection, scattering, diffraction, and so on. So you've got a time dispersion phenomena here where the signal is dispersed over a period of time. So you can interfere the signal with neighbor symbols, or it's called inter-symbol interference, or the signal reaches a receiver directly, and because of reflection from an object is phase shifted. So the effects of multipath are that the receiver can actually get multiple copies of the signal. Each are following a different path. So for example, here you have the original signal because it's a line of sight, and then you have a degraded signal, which comes from a reflection of the original signal from a wall, for example. And the degraded signal has a different phase than the original signal. And these two are, they are composing themselves at the receiver. So it might look like something like this. This is the original signal. This is the phase shifted signal, and whenever they reach the receiver, they can compose. So the copies can either strengthen or weaken each other, depending on, of course, the different aspects of the environment. And if there are in or out of phase, then you can have some very interesting effects for transmission, where even if you have line of sight, due to a lot of reflections through walls, you can actually get a very degraded signal, and you cannot actually communicate between the devices. So for example, you can have nodes that are as close as maybe 2 meters or 4 meters. So you can actually have direct line of sight between them, but there's no radio communication possible because of the environment. So the effects of mobility, what happens when the actual nodes move within this environment? Well, that means that the channel characteristics, the communication channel changes over time and location. The paths of the signal changes. There are different delays happening. There are different phases of the signals. There are very quick changes in the receive power. It's called short-term fading, which all affect the communication from the signal. So fading, for example, is the time variation of the received signal strength that is caused by changes in transmission medium or different paths of the signal. So, for example, you have rain coming in, you have moving objects that might come in between the receiver and the transmitter. If you've got a moving sender or receiver, you have a lot of variations and a lot of variables that can actually affect your communication. There are additional changes in how the distance to the sender actually varies, obstacles further apart, changes in the average power received, and so on. So you can have a receive power which varies wildly in relationship to time when you have moving receivers and transmitters. So what this all leads up to is the fact that radio spectrum communication might be impeded by a lot of factors, so a lot of variables. Again, you might have radio irregularity, for example, where a radio range is not isotropic, so it cannot be approximated to a sphere. You can actually have a medium where an electromagnetic signal propagates, and the signal might be diffracted, reflected, or scattered on the different surfaces, and then what happens is it changes in amplitude depending on the direction of propagation. So that leads to an anisotropic signal. So which means that it's opposite to isotropic. It's different in directions, or it has a directionality to it. And the signal strength for this type of radiator is different in different directions. So if you orient the device in a certain direction, you get a certain receive power. If you maybe rotate it or maybe changes its position, then you will get a different receive power. And you have some examples here of signal strength, which is varying for a receiver when you actually orient the receiver in different directions. So you just rotate the receiver into the 4 cardinal directions, north, south, east, and west, and you measure the receive power over time. And you can see that you've got a higher RSSI when the device it's in the south position, and a very low RSSI when the device is in the east position. So just by rotating the device, you will change the actual receive power for the radio signal, which means that it has a directional antenna. So it has an antenna which actually has a preference of a certain direction for reception. You can have a stronger actually received signal in a certain direction. So again, this affects, of course, the capability of communicating through the communication channels. You have bit error rate, a higher bit error rate as the received signal strength is lower, and you also have higher packet loss ratio. So for example, for the example in the previous slide, you might have a higher packet loss when the distance between the receiver and the transmitter is higher, and you are actually using the, let's say, east variation, where you have the lowest RSSI possible here. So you will have a higher packet loss whenever you do this. So the packet reception ratio is a lot smaller. You will lose a lot of packets. So whenever you do this, you can actually plot, you can make something like a 360 plot of the received power for the antenna. And this gives you a communication range basically for a certain radio emitter or receiver. So by plotting it like this, you will see the power in different orientations, in different rotation angles, and you can actually see the very powerful directionality of the receiver itself. Okay, any questions so far? Okay, if not, thank you very much. I think we can finish for today.